Okay guys, good evening and welcome back to electric circuits. So we have been exposed to the notion of phasor, which is used to represent any sinusoidal current or a sinusoidal voltage. Yes or no? Any sinusoidal current or any sinusoidal voltage can be expressed as a complex number which is called the phasor. And we are quite comfortable in terms of going from time domain to phasor domain and also from phasor domain back to the time domain. So in this session we will get started with the actual circuit analysis at sinusoidal steady state, wherein we will try to find the various voltages and the currents assuming circuit has reached steady state. Okay. So let's start with something very basic. So this is the circuit, okay. So what circuit is this? It is a simple RL circuit where the resistor and the inductor are connected in series across a sinusoidal voltage source denoted by Vn. And what is the input voltage as a function of time? It is some Vp cos omega t plus theta. And the question is what to find VL of t, which is the voltage across the inductor as a function of time at steady state, So what steady state will this circuit reach at t equal to infinity or after a long time? Because the circuit is what driven by a sinusoidal source, it will reach sinusoidal steady state. And you know, at sinusoidal steady state, every voltage and every current is also going to be sinusoidal at the same frequency. Let us now do the analysis in the phasor domain. Okay, so in the phasor domain, you know, every element should be replaced with its impedance, and all voltages will become what? Phasor voltages, and all currents will become what? Phasor currents. Okay, so what will this circuit be in the phasor domain? The other name for phasor domain is what? The frequency domain. So when I say frequency domain, it is same as what? The phasor domain. So just now I told you what? In phasor domain, you should replace each and every element with its impedance. Okay, in the last lecture, we had looked at the concept of impedance. Impedance is what? The ratio of phasor voltage to the phasor current. What is the impedance of R? R itself. What is the impedance of the inductor? Is it not J omega L? Yes. So is it not going to be something like this? So there is what? R, whereas the inductor will have an impedance of J omega L, and then small Vn of t in the time domain will become what? Capital Vn. So capital Vn is what? The applied phasor input voltage. Similarly, small VL of t, which is what? The voltage across the inductor, is going to become capital VL. Capital VL is what? The phasor voltage across the inductor. Yes, so this is what? VL. So are we not having two impedances in series across a voltage source? If you have two impedances in series across a voltage source, what takes place is what? Voltage division. Voltage division will take place. Okay, so here you can call this R as what? Z1. You can call this J omega L as what? Z2. So it is like having two impedances in series, Z1 and Z2, across a voltage source Vn. So from voltage division, okay, from voltage division, don't we get VL, which is the drop across Z2, will it not be equal to Vn times Z2 by Z1 plus Z2? I mean, this is simple voltage division applied to what? Two impedances. Earlier, we used to apply the same voltage division for resistors, yes, on R1, R2 connected in series across a voltage source and so on. This time we have what? Two impedances, but the principle will remain the same. Okay, there we have resistances, now we have what? Impedances. Whether it is the resistance or the impedance, both will obey what? Ohm's law. So nothing is going to change. Okay, so the phasor voltage across the inductor will be what? Vn times Z2 by Z1 plus Z2, where Z2 is what? J omega L, and Z1 is what? R itself. And what about capital Vn? Capital Vn what is this voltage in the phasor domain? Is it not simply Vp angle theta? Yes or no? Vp cos omega t plus theta in the phasor domain is going to be equal to what? Vp angle theta. So capital Vn, it is what? Vp angle theta. Okay. Anyway, we'll just go to the next slide. So here VL is equal to what? Vn times Z2 upon Z1 plus Z2. And just now we found that the phasor input voltage is simply equal to what? Vp angle theta. Z2 is what? The impedance of the inductor, which is J omega L, upon Z1 plus Z2, which is R plus J omega L. R plus J omega L. Now if you look at the numerator, Vp angle theta is what? Polar form. J omega L, what is J omega L in polar form? Is it not omega L angle 90 degrees? Yes or no? J omega L is same as what? Omega L angle 90 degrees. Okay, so this can be written as what? Vp times omega L times angle theta and also angle 90 degrees, because J is simply equal to what? Angle 90 degrees. And then if you look at the denominator, what is the denominator? It is R plus J omega L. Again, R plus J omega L, clearly it is in rectangular form, which can be expressed in polar form. Polar form means what? Magnitude followed by the phase angle. What is the magnitude of this complex number in the denominator? Square root of R square plus omega square L square. So square root of R square plus omega square L square, followed by the angle of this complex number. Angle of any complex number, you know, is equal to what? Tan inverse imaginary part divided by real part. So what is the angle of this? Tan inverse imaginary part is what? Omega L. Real part is what? Just R. So tan inverse omega L divided by R. That's all. Now this can be expressed as what? Vp omega L divided by square root of R square plus omega square L square, and then angle 90 degrees plus theta minus tan inverse omega L by R. I mean, in the numerator you have product of two angles, you can just add the angles. Once you add the two angles in the numerator, that is what? Theta plus 90 degrees, which I wrote as what? 90 degrees plus theta, then you should subtract the denominator angle from the numerator angle. That's what I did here. 90 degrees plus theta minus tan inverse omega L by R. So now, are we not having the phasor voltage across the inductor in standard polar form? Yes. So this entire thing, which is what? Vp omega L divided by square root of R square plus omega L square, it is like amplitude, whereas this entire thing, it is like the angle. Which angle? The phase angle. Once you have any phasor in the polar form, you can very easily go back to time domain, because the question is what? To find VL of t, voltage across the inductor, as a function of time at steady state. But right now we only know the phasor voltage across the inductor, which should be converted into what? Time domain. And how would you do it? So capital VL will become what? Small VL of t. I mean, it is going to be equal to what? Amplitude times cos of omega t plus the phase angle, whatever is the phase angle. Okay, so what is the amplitude? This entire thing is what? The amplitude, which is Vp omega L divided by square root of r square plus omega square L square times cos of, first you have to write omega t, and then you add the complete phase angle to this omega t. Okay, so cos of omega t plus 90 degrees plus theta minus tan inverse omega L by r. Okay, this is the thing. I hope it is clear. See, more than the final expression for the voltage across the inductor as a function of time, you should be clear about the approach. So the given original circuit has been redrawn in the phasor domain. So and in the frequency domain or in the phasor domain, we simply replace every element with its corresponding impedance, and also every voltage will become what? A phasor voltage, and every current would become a phasor current. Then we deal with everything in terms of what? Complex numbers, because impedance is what? Complex. Phasor voltage, phasor current, everything is what? Complex. So once you do the analysis in terms of what? Complex numbers, in the end you will get the phasor voltage or the phasor current. Convert that final phasor quantity into time domain so as to get the voltage or the current as a function of time. In fact, this is the standard recipe for solving any circuit driven by sinusoidal sources. We always do the analysis in the frequency or the phasor domain, and in the end we will just come back to time domain. This is much easier. Okay, I hope this problem is clear. Okay, I forgot to make one simple yet important point. I told you what? Impedance is very much similar to resistance, and the inverse of impedance is what? Admittance, which is very much similar to conductance. Yes or no? Yes. So let's say we have three elements in series. Look at this. There are three elements in series. You see, when you have three resistors in series, can't we simply add the three resistances? Yes or no? When you have three resistors in series, you can simply add the three resistances. In the same way, if you have three impedances in series, let's say they are what? Z1, Z2 and Z3, all connected between what? A and B. You can replace these three impedances in series with one single impedance between A and B, whose value is going to be Z1 plus Z2 plus Z3. So it is similar to having what? Three resistors in series, R1, R2 and R3, where the net resistance would be what? R1 plus R2 plus R3. So it is very much the same as having three resistors in series. Okay, because impedance is same as what? Resistance. Okay, so A, B, and this is what? Z1 plus Z2 plus Z3. Okay, and then the other connection is what? Parallel connection of elements or parallel connection of impedances. Okay, so this time let's say we have three elements connected in parallel. Okay, three elements connected in parallel. Let all of them be connected between the same 2 points A and B. So for the first element, let the impedance be Z1. For the second element, let the impedance be Z2. And for the third element, let the impedance be Z3. So when I write ZAB, ZAB is what? The net impedance between A and B. So how do you find, or how do you get the expression for ZAB? Say having three impedances in parallel is same as what? Having three resistors in parallel. Just imagine if you have R1, R2 and R3 all connected in parallel, how do you find the equivalent resistance? 1 by R equivalent is equal to what? 1 by R1 plus 1 by R2 plus 1 by R3. So we should do a similar thing here also look at this. So here also 1 by ZAB. 1 by ZAB is similar to what? 1 by R equivalent. So ZAB is what? The net impedance between the 2 points A and B. Okay. So 1 by ZAB, it will be equal to what? Like just like 1 by R equivalent is what? 1 by R1 plus 1 by R2 plus 1 by R3. 1 by ZAB would be 1 by Z1 plus 1 by Z2 plus 1 by Z3. Again, inverse of impedance is what? Admittance, right? So 1 by ZAB, is it not same as YAB? So just like ZAB is what? The net impedance between the two points A and B. YAB is what? The net admittance between A and B. Again, 1 by Z1, is it not same as Y1? 1 by Z2 is what? Same as Y2. 1 by Z3 is same as what? Y3. So what is the point here? When you have elements connected in parallel, it is much easier to find the net admittance. You can simply add up the admittances. So in parallel, you can add the admittances. In series, we can add the impedances. Again, an extremely trivial point. So in parallel, it is easier to find the overall admittance by simply adding the various admittances connected in parallel. And in series, it is easier to find the net impedance, and that is by simply adding all the impedances connected in series. I hope this point is clear. We'll take up one more example. Okay, just look at the circuit here. So there is some network. Is it not a linear network? Because look at the various elements present in the network. We have two resistors. One is what? 1.5 kilo ohm resistor. The other one is what? A 1 kilo ohm resistor. We also have the two energy storage elements. First is what? The inductor, whose inductance is what? 1 by 3 Henry. And the next one is what? The capacitor, whose value of capacitance is what? 1 by 6 microfarad. And then this network is connected across a sinusoidal voltage source whose value is what? 40 sine 3000 T volts. 40 sine 3000 T volts. You have to find I of t at steady state. You see, look at what this I of t is. What is this I of t? Is it not the current drawn by this yellow color network? Because after all, the source is what? Connected across the yellow color network, and the yellow color network will definitely draw some current from the source which is driving the network. So what is the current drawn by this yellow network or yellow color network at steady state? Once again, we should do the analysis in the phasor domain, because directly they are saying what? Find I of t at steady state. At sinusoidal steady state, all currents and voltages are going to be sinusoidal. So we can conveniently do the analysis in the phasor domain. So number one, what is the operating frequency of the circuit? I already told you, operating frequency of any circuit is same as what? The frequency of the input source that is driving the circuit. What is the input source driving the circuit? 40 sine 3000 T volts. You can think of it as what? 40 sine omega t. 40 sine omega t, where the value of omega, so what is the value of omega? 3000, right? So here omega, it is what? 3000 radians per second. That is the operating frequency of this circuit. And at this operating frequency, you should compute the values of the impedances of the inductor and the capacitor. Resistor impedance at any frequency is simply equal to what? The value of the resistance. Yes or no? 1.5 kilo ohm, that is also value of impedance at any frequency. 1 kilo ohm is also what? The value of the impedance at any frequency. Okay. So here ZL is what? The ZL is what? It is the impedance of the inductor. Yes, impedance of the inductor. What is ZL given by? Impedance of any inductor is what? Given by J omega L. So J times omega is what? 3000, and L is what? 1 by 3. So is it not J 1000 ohms? Yes or no? the impedance of the inductor at this operating frequency of 3000 radians per second, it is what? J 1000 ohms, or you can also say J times 1 kilo ohm, J 1 kilo ohm, okay? In the same way, we can also find, the impedance of the capacitor. What is the impedance of the capacitor? Given by 1 by J omega C. So ZC is what? 1 by J omega C. Again, 1 by omega is what? 3000, whereas the capacitance value is what? 1 by 6 times 10 power minus 6. 1 by 6 times 10 power minus 6. Again, 1 by 6, 1 divided by 1 by 6 is what? 6. Even 1 by 10 power minus 6 is what? 10 power 6. So I think it is 6000 by 3000. Not 6000. 6 into 10 power 6 by 3000. Will it not be 1 by J times 2 kilo ohms? Again, 1 by J, remember, is same as what? Minus J. So please verify that the value of ZC comes out as minus J 2000 ohms. That's all. ZL is what? J 1000 ohms positive, whereas ZC is what? Minus J 2000 ohms. Okay. Well, the way to proceed is what? I hope everybody has noted down the circuit diagram. Okay, now let us do the analysis in the phasor domain. When we are doing analysis in the phasor domain, we should replace every element with its impedance. Okay, and also the input source should be represented in terms of its phasor representation. Yes. So again, I've drawn the same, network. So 40 sine 3000t let this be IN. Let this be IN. Let this be Vn. Yes, Vn is what? The phasor input voltage. IN is what? The phasor input current. What is the ratio of phasor input voltage to the phasor input current? Is it not the input impedance? Yes, an input impedance. Okay. So here you can call this as what? A. You can call this as what? B. Yes. If you look at the yellow color network, is it not between these 2 points A and B? So there will be some net impedance between A and B, and that net impedance between A and B is what is called the input impedance. It is what? The input impedance. Okay. And here Z in, which is what? The input impedance, will be equal to what? The phasor input voltage divided by the phasor input current. So what is the phasor input current in terms of Vin and Zin? Again, Ohm's law, I is equal to what? V by R. But here in the phasor domain, IN will be equal to what? Vn divided by Zn. Yes, IN will be equal to what? Vn divided by Zn. So it's all about finding the input impedance of this yellow color network. Again, input impedance is what? Simply the equivalent impedance between A and B. Using series and parallel combination of impedances, you can compute the equivalent impedance of this yellow color network between the 2 points A and B. Okay. I think already we know the values of ZL and ZC. Yes. ZL is what? J 1000. So in the phasor domain, inductor will become an impedance of value J 1000 ohms. And what about the capacitor? ZC is what? Minus J 2000 ohms. Okay. Even the capacitor will become an impedance of value minus J 2000 ohms. Now if you look at the 1 kilo ohm resistor and the capacitor, both are in series, right? So if you have two impedances in series, you can simply find the net impedance by adding the two impedances, okay? And look at this branch and the inductor, both are in parallel, yes or no? This entire branch containing what? The resistor in series with capacitor. This branch and the inductor both are in parallel. If you have two branches in parallel, how do you find the net impedance? Z1, Z2 by Z1 plus Z2, yes or no? So here what you can do is the following, yes. So for this, let it be Z1, and for this part, let it be Z2, okay. So is it not going to be this, the input impedance, which is same as what? The net impedance between A and B, it will be equal to 1.5 kilo ohms plus the parallel combination of Z1 and Z2. So it is what? Z1 parallel Z2. I hope this makes sense. 1.5 kilo ohms plus Z1 parallel Z2. So what is Z1? Let me write that. Z1 is simply the impedance of the inductor, which is J 1 kilo ohm. What is Z2? Z2 is what? The impedance of the series combination of the 1 kilo ohm resistor and the capacitor. Just add the two impedances, 1 kilo ohm minus J2 kilo ohms, okay? So 1 kilo ohms minus J2 kilo ohms. So these are the values of Z1 and Z2. You can easily find Z1 parallel Z2 value, Z1 Z2 divided by Z1 plus Z2. So in that way you will get the value of Z1 parallel Z2. Then you add 1.5 kilo ohms to it. Then you will get the net impedance between A and B, which is also going to be the input impedance, seen from the input source point of view. That means from the input voltage source point of view, this entire yellow color network will appear like a single impedance of value Zn. So it is as if a single impedance of value Zn is connected across the source. So obviously the current drawn by the impedance would be what? The applied input voltage, that is what? Capital Vn divided by the input impedance. That is how we will finally find the current. Someone get the value of the input impedance. Please tell me the input impedance in polar form. I want the input impedance in polar form. Input impedance in polar form, it means what? Magnitude followed by phase angle. I want the input impedance in polar form. Okay, Dineshwaran is saying 2.25 at an angle approximately 36 degrees. Units, is it not kilo ohms? It should be kilo ohms because here everything is in kilo ohms. Even the resulting input impedance would be in kilo ohms. So Zn, I believe this is correct. 2.25 kilo ohms at an angle 36 degrees. Let's call it 36 degrees, okay? I hope others are also getting the same thing for the input impedance, okay? So what is input impedance? 2.25 at an angle 36 degrees, units kilo ohms. Units kilo ohms. Okay, Aditya Singh is saying that the input impedance is about 2.25 at an angle 36.86 degrees kilo ohms. Okay, I will go with this thing, 2.25 at an angle 36.86 degrees. I'll just modify this. 2.25 at an angle 36.86 degrees, units kilo ohms, okay? That's all. See, now the thing is what? as I already explained, it is like having a single impedance. Okay, the entire yellow color network can be replaced with a single impedance denoted by Zn, and as you said, the Zn value is what? 2.25 at an angle, how much? 36.86 degrees. 36.86 degrees kilo ohms. Okay, and then this input impedance or the single equivalent impedance is what connected across the sinusoidal voltage source. What is the value of the sinusoidal voltage source? 40 sine 3000 t volts. Okay, and this current is what? The phasor current is what? IN. So this is what? IN. Okay, so obviously this is going to be capital Vn. As we already know, the phasor input current will be equal to what? The phasor input voltage that is applied divided by the input impedance, which is what? Zn. Okay, so from here I think directly we can write the input current as a function of time. So would it not be 40 divided by 40 volts divided by 2.25 kilo ohms, and then sine of 3000 t minus 36.86 degrees. Yes, what is 40 by 2.25? 40 by 2.25. Yeah, is it 2.25 or 2.5? Please check once. What about others? Pooja, Shivasainath. What is the input impedance? Is it 2.25 or 2.5? 2.5, yes. So it is what? 2.5 kilo ohms at an angle 36.86 degrees. Okay, cool. So here also we should change it to what? 2.5. Even here it becomes what? 2.5. Again, what is 40 by 2.5? 40 by 2.5 is what? 16, correct? 40 by 2.5, it must be 16. What about the units for the resulting current? Look at the current expression, volts divided by kilo ohms. Volts by kilo ohms, the current must be in milliamps, right? So it is going to be 16 sine 3000 t minus 36.86 degrees, units milliamps. Okay, so please tell me, is the input voltage leading or the input current leading? Is the input voltage leading or is it the input current that is leading? Which one is leading? Please type in the chat box. Which one is leading? Is it the input voltage or the input current? Voltage, right? See, what is the input voltage? 40 sine 3000 t. 40 sine 3000 t. So what is the phase angle of the voltage? It is 0 degrees. What is the current? 16 sine. First of all, if you recall, I told you what? If you want to directly take the difference between the two phases, both the quantities should be expressed in terms of what? Sine or cosine. Both should be sine or both have to be in terms of cosine, and also the amplitude must be positive. And here the input voltage is what? 40 sine something, and the input current is what? 16 sine something. So both amplitudes are what? Positive. Both are in terms of what? The sine function. You can simply take the phase difference. Okay, so the input voltage phase angle is what? 0 degrees, whereas the input current phase angle is what? Minus 36.86 degrees. Clearly 0 degrees is what? More than minus 36.86 degrees. So as you all said, input voltage will lead the input current. So here Vn leads In. In fact, by how many degrees? Vn leads In by 36.86 degrees. VN leads IN by 36.86 degrees. Now for which element voltage leads current? We have three basic elements, right? Resistor, for which voltage and current will be in phase. Capacitor, for which current leads voltage by 90 degrees. Inductor, for which voltage leads current by 90 degrees. And here our input voltage is going to lead the input current. So the overall nature of the network, the overall nature of the yellow color network is what? Inductive. The overall nature of the yellow color network is what? Inductive, because the input voltage is leading what? The input current. Yes, it is not purely inductive. Had it been purely inductive, then the input voltage would lead the input current by exactly 90 degrees. But here the input voltage, yes, it is leading the input current, but not by 90 degrees, by an angle which is less than 90 degrees. That means what? The overall nature of the yellow color network is what? Inductive. Yes, that's the bottom line. Okay, and this is the current expression. I hope the method is clear. Okay, in fact, if you look at the impedance, see, impedance angle. What is the impedance angle? What is the impedance angle? Zn is what? 2.5. 2.5 is what? Magnitude. 2.5 kilo ohms is what? The magnitude of the impedance. Whereas 36.86 degrees is what? The angle of impedance. Angle of the input impedance. In fact, the angle of input impedance, is it not the phase difference between the input voltage and the input current? Because after all, Zn is what? Vn divided by In. And this also means what? Angle of Zn will be equal to what? Angle of Vn minus angle of In. So here itself you can see that angle of Zn is what? Positive. That means the phase difference between the input voltage and the input current is what? Positive. In other words, the input voltage will lead the input current by an angle which is equal to what? The angle of the input impedance. So always the angle of the input impedance will directly tell you whether the input voltage will lead or lag or be in phase with respect to the input current. You understood? Yes. Okay, let's take up another simple example. So there is some network which contains what? Two sources. One is what? A sinusoidal voltage source denoted by Vs. Another is what? The sinusoidal current source denoted by Is. And apart from the two sources, we also have some passive elements, two resistors, one inductor and also one capacitor. Capacitor value is what? 1 farad, and the current through this capacitor is what? IC, and the operating frequency of this circuit is what? 2 radians per second. So you can assume that both the sources, that is what? Vs and Is, are at the same frequency, and that is how much? It is 2 radians per second. Okay, that is the operating frequency of the circuit. Now capital IC. What is capital IC? Is it not the phasor current through the capacitor? If capital IC, that is what? The phasor current through the capacitor is what? 2 at an angle 0 degrees amperes. The question is what? To find Is of t. To find Is of t. Is is what? The value of the sinusoidal current source. Do it. Please type the expression for Is of t, that is the value of the sinusoidal current source as a function of time, in the chat box. Please type it. Remember what is given? The phasor current through the capacitor is given. Whenever you are given the phasor current, that means what? You are dealing with things not in the time domain but in the phasor domain. So once again, you should do the analysis in the phasor domain, but in the end you should come back to our time domain. Only then you will be able to get the write the expression for Is of t. Do it. You see, it's very simple. We just have to do the analysis in the phasor domain. I think very good. Dineshwaran, what you got is correct. 2.06 at an angle, I think minus 14 degrees. Correct, right? Yes. So how do you go about analysis in the phasor domain? Whenever you are doing analysis in the phasor domain, you should first replace every element with its impedance, okay? So here ZC is what? The impedance of the capacitor, which is always going to be 1 by j omega c. 1 by j times omega. What is omega? The operating frequency, which is 2, times the capacitance, which is what? 1. So is it not 1 by j2? Yes. So it is what? 1 by j2 ohms. Even the small IC in the phasor domain will become what? Capital IC. And 1 farad capacitance in the phasor domain will become an impedance of value 1 by j2 ohms. Now can't you write the phasor voltage across the capacitor? Again, Ohm's law. Phasor voltage across any impedance will be equal to what? The impedance multiplied with the phasor current. What is the phasor current? 2 at an angle 0 degrees. Okay, so the capital IC value is what? 2 at an angle 0 degrees, which is same as what? 2 amperes, because angle 0 degrees is what? Just 1. Okay, so what is the phasor voltage across the capacitor? Phasor current, which is 2, multiplied with the impedance of the capacitor, which is 1 by j2. So is it not 2 into 1 by j2? 2 into 1 by j2, 2 and 2 will get cancelled. Is it not 1 by j? 1 by j is what? Minus j. Yes. So this phasor voltage drop is what? Minus j volts. 1 by j volts. It is same as what? Minus j volts. Now the drop across the 2 ohm resistor is also going to be minus j volts, because after all, the 2 ohm resistor, it is in parallel with the capacitor. Always they'll have the same voltage drop. And also this small is in the phasor domain is going to become capital Is. Okay, if you know the voltage across any resistor, can't you write the current flowing through the resistor? So how much is the phasor current flowing through the resistor of value 2 ohms? The phasor voltage divided by resistance. Phasor voltage divided by resistance is what? Minus j by 2. Let me write it properly. Minus j by 2. Now if you look at this point, at this point, Is is what? Entering minus j by 2. By the way, this minus j by 2 units are what? Amperes, right? Yes. So at this point, minus j by 2 is what? Leaving. IC is also what? Leaving. Is is what? Entering. Yes. So if you write KCL at this point, won't you get Is is equal to what? Minus j by 2 plus the phasor current through the capacitor, which is given as 2. So minus j by 2 is what? Minus 0.5 j. So is it not same as 2 minus 0.5 j? That is what? Is. What is this 2 minus 0.5 j in the polar form? 2 minus 0.5 j. First of all, 2 minus 0.5 j lies in this phasor will lie in which quadrant? 2 is what? Real part, positive. Minus 0.5 is what? The imaginary part, negative. Real part positive, imaginary part negative. So this phasor, capital Is, would it not lie in the 4th quadrant? And any phasor that lies in the 4th quadrant, the angle would lie between 0 degrees and minus 90 degrees. Okay, you can easily express the same complex number in its polar form, so that you will get capital Is in the polar form. Once you get capital Is in the polar form, because the ultimate goal is to write Is as a function of time. Once you have capital Is in the polar form, phasor current in the polar form, you can go back to time domain. Okay, so now I believe this 2 minus 0.5 j is equal to 2.06 at an angle minus 14 degrees amperes. So clearly the phasor current Is, capital Is, is now in the polar form. Once you have it in the polar form, we can go back to time domain, small is of t. So this 2.06 is going to be the amplitude, minus 14 degrees is going to be the phase angle of the sinusoidal current. Yes. So 2.06 cos of omega t. First you always have to write what? Omega t. Remember omega is what? 2. So omega t is going to be 2t. Yes. So 2.06 times cos of 2t, and then you add whatever is the phase angle, which is minus 14 degrees amperes. I hope all of you got the same expression for is of t. 2.06 cos 2t minus 14 degrees amperes. Okay. Try this one. So once again we have a linear network containing what? A capacitor, a resistor, and also an inductor. And for all the three elements, the corresponding impedance values are given. For the capacitor, the impedance value is what? Minus J5 ohms. And for the resistor, impedance is what? 5 ohms. And for the inductor, the impedance is what? J5 ohms. Okay. And this network is connected across a sinusoidal voltage source whose phasor value of voltage is what? 100 angle 0 degrees volts. Okay. I1 is what? The phasor current through the capacitor. I2 is what? The phasor current through the resistor. I3 is what? The phasor current through the inductor. So you should find all the three phasor currents in polar form. Polar form means what? Magnitude followed by phase angle. Okay. In fact, what is this I1? Is it not the current drawn from the source? Current drawn from the input source. Current drawn from the input source, is it not same as the input current? And what is the input current going to be? Input current is always going to be what? The input voltage or the phasor input voltage divided by the input impedance. Yes or no? Phasor input voltage divided by the input impedance, because the very definition of input impedance is what? Capital Zn, Zn is equal to what? Capital Vn, phasor input voltage, divided by capital In, phasor input current. Okay. Please copy this down. So here again you can think of, you can think of this entire yellow color network as a one port network. Yes, for this yellow color network, this is what one terminal, this is what the other terminal. So clearly we have two terminals, and these two terminals will form what? A port. And this 100 angle 0 degrees, it is like the phasor input voltage applied across this yellow color one port network. Okay. And this phasor input current, let it be denoted by In. And here you can note that this In is same as what? I1. Yes, on In is same as I1. Now for this yellow color network, won't there be an input impedance? Yes or no? Yes. For this yellow color network, there will be an input impedance. Okay. So once you calculate the input impedance, you can find the input current, that is what? Capital In. As we already know, capital In will be equal to what? The phasor input voltage, which is already given 100 at an angle 0 degrees, divided by the input impedance. How do you calculate the input impedance? First of all, these two impedances are in parallel. Club them into what? A single impedance. Then this parallel combination, it is in series with this impedance. Add the two impedances, then you will get the input impedance. Okay. So what we will do, I hope everybody understood this. Okay. This parallel combination of the resistor and the inductor, let it have an equivalent impedance of Z1, and let the capacitor alone have an impedance of Z2. Now Z2 and Z1 both are in series. In fact, this input impedance, which is the net impedance between these two terminals, will be equal to what? Z2 plus Z1. Okay. So here Zn will be equal to what? Z1 plus Z2. So now we should find Z1. Z1 is what? Parallel combination of these two. Will it not be 5 multiplied with J5 divided by 5 plus J5? Yes, 5 times J5. 5 is what? Common to both numerator and denominator. You can directly write the numerator as what? 5J or J5 divided by 1 plus J. J5 divided by 1 plus J. I'll just leave it like that. And then our input impedance, what is it? Input impedance is what? Z1 plus Z2. Remember, Z2 is what? The impedance of the capacitor, which is already given as minus J5 ohms. So to this minus J5 we add this Z1, which is this much. Okay. So minus J5 plus J5 upon 1 plus J. Correct? Okay. Now if you take LCM and so on, first it will be minus J5. What is minus J square? J square is what? Minus 1. Minus J square is what? Plus 1. So plus 5. Again plus J5 divided by 1 plus J. You see this minus J5 and plus J5 both will get cancelled out. Minus J5 and plus J5 will get cancelled out. What is left in the numerator? Only 5. And 5 divided by 1 plus J. Again 5 is what? 5 at an angle 0 degrees. 1 plus J. 1 plus J. What is 1 plus J in this thing? What? Polar form. 1 plus J in polar form is what? Root 2 at an angle 45 degrees. Yes. So 1 plus J is same as what? Root 2 at an angle 45 degrees. That's all. 5 divided by root 2 at an angle minus 45 degrees. This is my input impedance in polar form. Okay. What is it? 5 by root 2 at an angle minus 45 degrees. Units, they are going to be ohms. Impedance, right? Units are going to be ohms. I hope this is correct. Okay. So just tell me, what is the overall nature of the yellow color network? Is it capacitive or inductive? What is the overall nature of the yellow color network? Is it inductive or capacitive? I told you what, you should simply look at the angle of the input impedance. What is the angle of the input impedance? Minus 45 degrees. Angle minus 45 degrees, that means what? Phase of the input voltage minus the phase of the input current is what? Minus 45 degrees. That means phase of input current minus phase of input voltage is what? Plus 45 degrees. Whenever input impedance angle is what? Negative. That means IN leads VN. IN leads VN. If IN leads VN, that means the overall nature of the yellow color network is what? Capacitive. Yes or no? Current leads voltage. That is what? The nature of a capacitive network. Current leads voltage by 90 degrees. It is what? Purely capacitive. But here, current leads voltage by 45 degrees. The overall nature of the network is what? Capacitive. Okay. So this is going to be capacitive in nature. That's all. Once you get the value of the input impedance, can't you find the input current? Because you know, input current will be equal to what? Input phasor input voltage. Again, 100 angle 0 degrees is same as what? Just 100 divided by 5 by root 2 at an angle minus 45 degrees. What is 100 by 5? It is 20. Even root 2 will go to the numerator. So again 100 is what? 100 angle 0 degrees. If you subtract the numerator angle and the denominator angle, won't you get angle plus 45 degrees? So would it not be 20 root 2 at an angle 45 degrees? 20 root 2 at an angle 45 degrees. I hope you also got the same thing. So there is what? The input current. Remember, the input current is same as what? The phasor current flowing through the capacitor. What will happen to this input current? Will it not get divided between this branch and this branch? Yes or no? This IN, yes, this IN will get divided between the resistor and the inductor. Current getting divided between two impedances connected in parallel. Is it not current division? So now we should apply what? Current division, so that we can get the expressions for I2 and I3. Okay. Anyway, the input current is what? This much. 20 root 2 at an angle 45 degrees amperes. 20 root 2 at an angle 45 degrees amperes. Okay. So it is like this. So IN is what? 20 root 2 at an angle 45 degrees amperes. Okay. Now I2 is what? The current through the 5 ohm resistor. In case of current division for two impedances connected in parallel, current through one impedance will be directly proportional to what? The other impedance. In this case, current through 5 ohms would be directly proportional to what? The other impedance value, that is what? J5. So I2 will be equal to what? First you write down the current that is actually getting divided, which is what? IN. IN into J5 divided by 5 plus J5. Yes. Now already we know the phasor input current is what? 20 root 2 at an angle 45 degrees. Again, J5 divided by 5 plus J5. 5 is common, 5 will get cancelled out. J alone is same as what? Angle 90 degrees. Yes. Again 1 plus J, what is 1 plus J? Is it not root 2 at an angle 45 degrees? And now what? This 45 degrees and this 45 degrees both will get cancelled. Root 2 and root 2 also will get cancelled. So what is our expression for I2? I2 is what? The phasor current through the 5 ohm resistor or the 5 ohm impedance. I2 is what? 20 at an angle 90 degrees amperes. Okay. And remember, this IN is same as what? I1. IN is same as what? I1. The only remaining current is what? I3. Again, I3 is what? The current through the inductor. Again, we will apply current division, or you can also write KCL. Because anyway at this point, IN is what? Entering, which will split into what? I2 and I3. Since already we know both IN and I2, I3 can be written as what? IN minus I2. But I will apply what? Current division. You can also get it by subtracting I2 from IN. IN minus I2 will be what? I3. So if you go by current division, what are you going to get? I3, which is what? The current through the J5 ohm impedance. Would it not be proportional to 5 ohms? First you write IN, because it is IN that is getting divided between the two impedances. So IN times 5 again divided by 5 plus J5. Again IN is what? 20 root 2 at an angle 45 degrees. Again divided by 1 plus J, right? 1 plus J is what? Root 2 at an angle 45 degrees. So now also you can see that root 2, 45 will get cancelled. The only thing that would remain is what? 20. If you want, we can write it as 20 angle 0 degrees amperes. So these are the final values of I1, I2 and I3. Capital I1, capital I2 and capital I3. Capital I1 is same as what? The phasor input current, which is 20 root 2 at an angle 45 degrees amperes. I2 is what? The current through the resistor, which is 20 at an angle 90 degrees amperes. I3 is what? The current through the inductor, which is 20 at an angle 0 degrees amperes. Okay. Okay, for this circuit, we will just try to do nodal analysis. You know nodal analysis, right? Nodal analysis is based on writing KCL at the various nodes, and when we perform nodal analysis, we will first find the various node voltages, and from the node voltages, you know, we can find the branch voltages, and from the branch voltage we can find the branch currents. This is the sort of flow we have when we approach the analysis using what? Nodal analysis method. Yes. What is the first step in nodal analysis? So here, by the way, every element is represented as an impedance. Okay, the component values are not given. Directly the impedance values are given. For example, for the capacitor, impedance is given. For the inductor also impedance is what given. In fact, for every element impedance is given, and this network, as you can see, is being driven by two sources. In fact, both are sinusoidal current sources. So this one is what? A sinusoidal current source, whose phasor value of the current is what? 1 at an angle 0 degrees amperes, and this one is what? 0.5 at an angle minus 90 degrees amperes. Let's perform nodal analysis. Well, if you want to perform nodal analysis in the phasor domain, first of all, you should choose one of the nodes to be ground or reference. Please tell me how many nodes are there in this network? How many nodes are there in this network? Don't you agree that there are 3 nodes in this network? The entire thing at the bottom is what? One node. And this thing is what? The second node. And this thing on the right will form the third node. So in this circuit there are 3 nodes. So how many nodal equations can be written? If the circuit has 3 nodes, how many nodal equations can be written? 2. Because one node will be chosen as what? Reference. You can always write a maximum of n-1 number of independent KCL equations. Okay. So the first step, okay, here let me write the goal itself. The goal is to perform nodal analysis in the phasor domain. Okay. Perform nodal analysis in the phasor domain. So the first step is to choose one of the nodes to be ground or reference. Just for convenience, I have chosen the bottom node to be our reference or ground. Okay. Once you choose this to be ground, you should assign voltages to all the remaining nodes. In this case, there are a total of 3 nodes. Already one node is what chosen to be ground or reference. Now we still have 2 other nodes. So let the voltage at this node be some V1. Let the phasor voltage at this node be some V2. So how many unknowns we have? We have 2 unknowns. Capital V1, which is the phasor voltage at this node with respect to ground. Capital V2 is what? The phasor voltage at this node, again with respect to ground. So to solve for 2 unknowns, how many equations are required? Obviously, you would need 2 equations. And how do you get those 2 equations? By writing KCL at each of the 2 non-reference nodes. Write KCL at this point. Also write KCL at this point. Okay. Look at this. Let's say we are writing KCL at the node where the voltage is what? V1. See, if you recall, the convention that we follow is what? If you are writing KCL at any node, we will always assume the current through any impedance or through any resistor connected to that node to be flowing away from the node. Yes, I mean to say this thing, like this, like this, like this. This current anyway is what? Entering, because this current is what? Already 1 at an angle 0 degrees. So if you look at this node, how many currents are flowing at this node? 5 currents, right? This is leaving, this is leaving, this is also leaving, this is also leaving. Only this is what? Entering. So what is KCL at this node? Sum of the 4 currents will be equal to what? The only incoming current. What is the current through the 5 ohm resistor in the downward direction? Would it not be this voltage minus this voltage divided by impedance V1 minus 0 divided by 5? Yes. V1 minus 0 divided by 5. What is this current going to be? V1 minus 0 divided by this impedance, which is minus J10. V1 minus 0 divided by minus J10. What about this current? This current is what? Current through J10 ohms from V1 to V2. So will it not be V1 minus V2 divided by J10? And finally, what is this current? This current is again flowing from V1 to V2. So it is going to be V1 minus V2 divided by, the impedance is what? Minus J5. Okay, now these 4 currents have been added, and the sum of these 4 currents will be equal to what? The only incoming current, which is what? 1 at an angle 0 degrees. Again, 1 angle 0 degrees is same as what? 1 ampere. I can just write it as 1 ampere. That's all. This is our first KCL equation. This is our first KCL equation. In the same way, we should also write KCL at the other node. Okay. So we have written KCL at this node, and the equation is what? This. Let us also write KCL at the other node. I already told you what? If you are writing KCL at any node, and if any impedance is connected to that node, we will take the current to be flowing away from that node through that impedance. Okay. So in that way, through this impedance, let's say the current flows like this. Through this J10 ohms, let's say the current flows away from this node, and through this J5 impedance also, let the current flow away from the node like this, and even this current is what? Flowing away from the node. What is the value of this current source? 0.5 at an angle minus 90 degrees. Angle minus 90 degrees, is it not minus J? Angle 90 degrees is what? Plus J. Angle minus 90 degrees is what? Minus J. So this is what? Minus J 0.5 amps. Okay. Now again, how many currents are flowing at this node? Clearly 5 currents are flowing at this node. 1, 2, 3, 4, 5. And you can see that all the 5 currents are leaving the node. All 5 currents leaving the node. So what is KCL going to be at this node? Sum of the 5 currents is going to be 0. So let us start with this current. What is this current? V2 minus V1. V2 minus V1 by minus J5. And then we should write this current, which is V2 minus V1 by J10 plus V2 minus V1 by J10. And then we should write about this current. What is this current? V2 minus 0 by J5. Sorry. So V2 divided by J5. And then we should write this current, which is V2 minus 0 by 10, or simply V2 by 10. And then finally we have this current, whose value is what? Minus J 0.5. So minus J 0.5 is equal to what? 0. That's all. These are the 2 KCL equations at the 2 nodes. Okay. And from these 2 KCL equations, we can solve for V1 and V2. Just 1 second. So the point is what? Whatever circuit analysis techniques we had for resistive circuits, all those techniques can be applied to circuits driven by AC sources, and especially when you are doing the analysis at sinusoidal steady state, wherein we replace all the elements with impedances. Once you replace the capacitor and inductor with impedances, then it is as good as a resistive circuit, because impedance obeys what? Ohm's law. Resistive circuits, all resistors also obey what? Ohm's law. Okay. So whatever we did for resistive circuits, all those techniques can be used in the phasor domain, because in the phasor domain, all elements become what? Impedances, which will obey some form of Ohm's law. Of course, it is related to what? The phasor voltage and the phasor current, not the actual voltage and the actual current. Phasor voltage will be proportional to phasor current, and this is in the frequency domain or in the phasor domain. Okay, let's take up one more example. So in the last example we had seen what? The application of nodal analysis. Now we will look at a case where we are going to apply the other technique, which is what? Mesh analysis. So this is the given circuit. So clearly in this circuit there are two meshes. What are the two meshes? This is one mesh, this is the other mesh. So if you have two meshes, you can write two mesh equations, and mesh equations are nothing but the KVL equation around every mesh. You can write KVL around this mesh, you can also write KVL around the other mesh. So what is the question here? Write the two mesh equations in phasor domain. So here you should write the two mesh equations in phasor domain. Write the two mesh equations in phasor domain. If you are doing analysis in the phasor domain, you should replace every element with its impedance. Yes. First of all, what is the frequency of operation? If you look at the only independent source connected to the circuit, is it not 10 cos 10 power 3t? Yes, the only independent source connected to the circuit is what? 10 cos 10 power 3t. So what is omega? In general, the source would be what? 10 cos omega t. In place of omega, we have what? 10 power 3. So here the frequency of operation, it is what? 10 power 3 radians per second. Frequency of operation is what? 10 to the 3 radians per second. So at that operating frequency, you should find the impedance of the inductor and also the impedance of the capacitor. ZL is going to be the impedance of the inductor. Is it not going to be J omega L? So J times 4 milli, right? No. First is what? Omega, which is 10 power 3, and then the inductance, which is 4 milli. 4 into 10 power minus 3. 10 power 3 into 10 power minus 3 is what? Just 1. So is it not going to be J4 ohms? What about the impedance of the capacitor? 1 by J omega C. Again 1 by J times omega. What is omega going to be? 10 power 3. And then C is what? 50 microfarad, which is 50 times 10 power minus 6. Again 1 by 10 power minus 6 is what? 10 power plus 6. 10 power 6 by 10 power 3 is what? 10 power 3. 1000 by 50 is what? 20. 1000 by 50 is what? 20. And 20 by J, which is what? Minus J 20 ohms. I hope these two values are correct. So ZL is what? The impedance of the inductor. ZC is what? The impedance of the capacitor. So for the inductor, let me write J4 ohms, and for the capacitor, let me write its impedance as what? Minus J20 ohms. And also, what is the value of the sinusoidal voltage source in phasor domain? 10 cos omega t. 10 cos omega t, is it not simply 10 angle 0 degrees? Yes. So this is going to be 10 angle 0 degrees volts. That's all. Now this small I1, will it not become capital I1? In fact, this I1, is it not the loop current of the first mesh? Or I1, is it not going to be the first mesh current? So this mesh current in the phasor domain would be capital I1. Let us call the second mesh current as what? Capital I2. So as you can see, we have two unknowns, I1 and I2. and if we can write the two mesh equations, we can solve for I1 and I2. That is what the two mesh currents. Okay. So let us write KVL around mesh 1. Let us write KVL around mesh 1. So how do you write KVL around any mesh? You start at some point, you go around the loop and come back to the same point. So if you start from here, as you go like this, are you not encountering minus first? So first you write minus and then the value of the voltage source, which is simply 10. 10 angle 0 degrees is what? Just 10. So first term is what? Minus 10. The next element is what? 3 ohm impedance or 3 ohm resistance, through which the current is what? I1. So minus 10 plus 3 times I1. Well, the next element in the first mesh is what? The 4 millihenry inductor, whose impedance is what? J4 ohms. But this inductor or this branch is what? Common to both the meshes. Whenever any branch is what? Common to the two meshes, that branch impedance should be multiplied with the difference between the two mesh currents. What difference? We are writing KVL for mesh 1. So this impedance should be multiplied with I1 minus I2. Okay. Plus the impedance, which is J4, times I1 minus I2 equal to what? 0. That's all. This is KVL around the first mesh. In the same way, we can also write KVL around mesh 2. So what is KVL going to be around mesh 2? KVL around mesh 2. Again, to write KVL around mesh 2, let us start from this point. So starting from this point, we will go around the loop in the clockwise direction. Okay. Again, as you go this way, this is the first impedance we will encounter. Again, this impedance is what? Common to mesh 2 and also mesh 1. But right now we are writing KVL for mesh 2. So this impedance should be multiplied with I2 minus I1. So J4 times I2 minus I1. And then the next impedance is what? The minus J20 ohms, which belongs only to what? Mesh 2. Just multiply the impedance with the mesh current. So minus J20 times the mesh current, which is what? I2. And by the way, this dependent voltage source, its original value is what? 2 times small I1. But in the phasor domain, small I1 has become capital I1. That is what? The first mesh current. So in the phasor domain, the value of the dependent source is going to be 2 times capital I1. I just replace small I1 with capital I1. Okay. That's all. So as you go like this, are you not encountering plus? Write down plus 2 I1 equal to what? 0. That's all. These are the two mesh equations from which we can solve for the two mesh currents I1 and I2. Again, this is just to illustrate the fact that all the techniques we have used earlier for resistive circuits, all those techniques can be used to do the analysis of our circuits driven by sinusoidal steady state, driven by sinusoidal sources, and when the circuit reaches what? Sinusoidal steady state. Okay.